Hello and welcome back everyone. Today, we are diving deep into the fascinating world of dynamic programming. Whether you are a coding enthusiast, a computer science student, or just someone curious about the magic behind efficient algorithms and problem solving, this video is tailor-made for you. Dynamic programming, or DP, is a powerful problem-solving technique using computer science and mathematics. I'm Brian Rad, and in this video, we will cover everything you need to know about dynamic programming, from the very basics to its practical applications. So grab your thinking caps because we are about to embark on a journey that will equip you with the skills to tackle complex problems efficiently. By the end of this video, you will not only have a crystal clear understanding of what dynamic programming is, but also will be armed with the knowledge and intuition to apply it to a wide range of challenges. So let's dive right in. Okay, we will start by demystifying the concept of dynamic programming. What exactly is it? And why is it such a powerful tool in the world of computer science and programming? Then we will explore how dynamic programming differs from another popular technique called divide and conquer. Understanding these distinctions will set a solid foundation for our journey. Next, we will delve into the core principles and techniques of dynamic programming. We will talk about mysteries of optimization, subproblem decomposition, and memoization that form the bedrock of this problem-solving paradigm. But theory alone won't do us much good, right? That's why we will roll up our sleeves and apply DP to some real-world problems. We will tackle the famous Fibonacci sequence, master the art of cutting rods efficiently, and unlock the secrets of finding the longest common subsequence in the strings. But first thing first, what exactly is dynamic programming? At its core, dynamic programming is a methodology for solving complex problems by breaking them down into simpler, overlapping subproblems. Each subproblem then is solved only once, with the result stored for future reference. Okay, so this definition that I just mentioned here for dynamic programming is just going to set the stage for us. And it's perfectly fine if it doesn't make perfect sense to you right now. We're going to make sure that we uncover the terms that we use in this definition and in a lot more details later in this video. But for now, a lot of people who get exposed to the topic of dynamic programming are wondering what the term programming here refers to. So the programming here does not refer to writing codes, as a lot of people might think intuitively. It comes from the mathematical programming. It means planning or optimizing a series of decisions. And then the term dynamic highlights the incremental nature of the solutions, where smaller subproblems are solved progressively. Dynamic programming can significantly improve the efficiency and performance of algorithms, making it an essential tool for tackling a wide range of computational problems. That brings us to the next thing here, which is what is the primary application area for dynamic programming. So dynamic programming is particularly well suited for solving optimization problems. You might ask, what are optimization problems? So these are problems where we seek to find the best possible solution, either to maximize or minimize a certain value. So if I want to give you an example here, imagine you're a business owner and you want to maximize your profit by choosing the best combination of your product to sell, considering production cost, market demand, and so on and so forth, in a way that encourages people to buy more from you so that it's going to maximize your profit at the end of the day. So now we also want to make sense of the difference between dynamic programming and divide and conquer. So far we grasped the essence of dynamic programming, but with drawing this comparison between dynamic programming and another similar problem-solving technique, divide and conquer, can help us further understand this particular problem-solving techniques here. So both of these techniques are valuable problem-solving approaches, but they shine in different situations. Understanding when to apply each approach is key to effective problem-solving. Divide and conquer, or DAC, divides a problem into subproblems and independently solves each subproblem. In DAC or DAC, what we really care about is making sure our subproblems cover the entire problem space. So we're looking everywhere for the optimum solution. But we don't really care about if we are solving the same problem more than once, or if our problems have overlaps of some kind. Probably because we can solve them independently or in parallel. Dynamic programming is all about taking this approach one step further, breaking a complex problem into smaller subproblems, and then solving each subproblem only just once. So again, in divide and conquer, we just want to make sure we find the optimum solution. We just want to make sure we are searching everywhere. Our subproblems altogether collectively covers the entire problem space, but we don't care if we are doing it efficiently or we are solving the subproblem only once. In dynamic programming, we want to make sure we don't do redundant work and we are as efficient as possible in order to solve all those subproblems. Okay. So the main distinction, therefore, here is dynamic programming is especially useful when your subproblems overlap or when you can optimize by avoiding redundant work. So if you have disjoint subproblems, divide and conquer will do just fine. Or if you do dynamic programming, you won't actually get so much improvement, right? Or maybe not any improvement at all, because your problems are disjoint, so they're not overlapping, and divide and conquer is solving them independently. Now, when your subproblems have some sort of overlaps, then dynamic programming actually can get the job done a lot more efficiently, and we're going to see how next. Therefore, if you have disjoint independent subproblems, you have the use case for divide and conquer. If you have some sort of overlapping subproblems, that's going to make the case. That's going to make a strong case for dynamic programming. Now, we already talked about what is dynamic programming and what is the main application area for dynamic programming. What's the difference between dynamic and programming and divide and conquer? Now we want to talk about the techniques in dynamic. How do we actually apply DP to solve real-world problems? So I have three techniques here. Technique number one, brute force. So that's not something new, but this is where all begins. You design a brute force recursive solution, tackling the problem heads on without any optimization. It's a straightforward approach that helps you understand the problem's structure. While brute force is not a dynamic programming technique, it's a technique that helps us put dynamic programming into work. After you do that, and after you get familiar with your problem structure, now you're kind of ready to start applying dynamic programming. And there are two ways you can apply dynamic programming. Well, number one is you take that recursive solution that you had, and this is where magic happens. So you take that recursive algorithm and you add a twist. You identify the overlapping subproblems, which are those that recur during the computation. Then you store the results of these subproblems, preventing redundant calculation in the future calls. It's like keeping a notebook of solutions, and it can dramatically improve efficiency. Memorization, by the way, if this is the first time you're hearing this, you might be wondering, oh, is that a typo? Are we talking about memorizing things? Because that feels like to be the right term here. So just to be clear, memorization is a technique used in computer science to optimize performance of functions by caching the result. While when we memorize things, it's technically the process of committing information to memory through repetition and practice. So these two are completely different. So when you actually memorize, you're storing data in a table or somewhere, and then you're retrieving that later whenever you need it. So it's quite different from memorizing things. So just in case, there is technically no typo here. Okay, so memorized. And then the third technique, this is actually all about so it's all about bottom-up approach. And whenever a lot of people, when they talk about dynamic programming, what they actually mean is the bottom-up approach. Okay, so this one's is all about intellectual reordering or proactively solving the problem. So I'm just going to keep the wording here consistent. So we try to find an intellectual order for these sub-problems in a way that we don't really need to look back and see if and make sure we are avoiding solving the same problem more than once. Okay, so instead of diving into complex sub-problems right away, you start with the simplest one. You progressively build up the solution to larger problems based on the solutions of smaller ones. It's like constructing a skyscraper from the ground up, ensuring stability and efficiency at each level. So these three techniques are the pillars of dynamic programming. Whether you're refining a brute force approach, memorizing solution to save time, or building your solution from the bottom, they empower you to tackle even the most complex computational problem with ease. Now, so we talked a lot about basically not a lot, but that was a decent amount of information about dynamic programming. But now let's actually see some examples, because at this point, if you're confused, that's probably the most normal feeling to have. And the only thing going to help is seeing a bunch of examples, and that's exactly what we're going to do next. Okay, so bear with me here. So the very first example, we want to start with something simple, and then we want to take it from there. So the very first example I have for you here is Fibonacci sequence. So given a number n, print the nth number in Fibonacci sequence. Okay, so if you don't remember Fibonacci sequence, I have it here for you. So this is actually how the sequence looks like. And I'm not going to get to the math or actually geometry behind this. But what you need to know here is that the sequence starts with a 0 and 1. And then afterward, each number is the sum of the previous two numbers. Okay, so for example, the third value here, 1, is the sum of 0 and 1, right? And then the sum of 1 and 1, that's going to give you 2. 2 plus 1 going to give you 3. 3 plus 2 going to give you 5. 5 plus 3 going to give you 8, and so on and so forth. So as long as you know that pattern, then you know how Fibonacci sequence works, and you have pretty much the idea to solve this problem. Now, in order for us to kind of build a habit of asking clarification questions, so I put this question in a vague form intentionally, so that I can encourage building that habit of getting things clarified first. So if you want to ask some clarification question here, some good examples would be, can n be a non-positive number? The answer is depends. When we say non-positive, it's both 0 and negative, right? N can be 0, but not negative. Next question might be, can we use additional data structure? yes, assume we want the fastest overall runtime. Therefore, if you want to use an additional data structure and that's gonna make things faster, by all means, go ahead. And one last question here might be, what should be the result when n is equal to 0? So as I just showed you the Fibonacci sequence, for this, the first element is 0, the second element is 1, and then afterward it's the sum of the previous two. Therefore, for n0, the output should also be 0. Okay, so let's see a bunch of examples super quickly. So if your input is, if n is 0, output is 0. So that's one edge case. The other edge case that does not kind of follow the Fibonacci formula is n equal to 1. So if n equals to 1, then your output should also be 1 because your sequence has now 0 and 1. And then let's also go with two middle case. N is equal to 2, and then n is equal to 9. So you see we have a bunch of elements in the sequence right now, and then we get the 9th element, which is 34. Okay, so we have everything we need, and now we need to think about our first brute force solution here. So we're always going to start with brute force. I know this might be an easy example, and you might already guess, or you might already have some great idea about the structure of this problem, but this is not always going to be the case, and brute force solution can actually help us to find out a structure. So let's start with that to see how that's going to work in practice. So the brute force here is going to be pretty straightforward. So we start with n, and then descending down, we recursively return the addition of the last and the second last member of our sequence. And what are your base cases? Your base cases are n equal to 1 and n equal to 0. So we're going to go all the way back until we hit the base cases, right? Okay, so let's put this into, let's code this up. So one simple implementation of this is going to look like this. So if you're dealing with the base case, n is equal to 0, output is 0, 1, 1. Therefore, if n is less than 1 or equal to 1, the output is going to be n, right? It's going to be itself. If not, we always gonna recursively call the previous two, basically. Sorry, we're gonna recursively make a call to n-1 and n-2. So technically, for n-1, this subproblem is 1 unit is smaller than the original one. For Fib n-2, this subproblem is 2 units smaller than the original problem that we're dealing with here. Now, the important question here is how efficient your brute force solution is, right? Because if your brute force solution is already great, is already super fast, then probably we're not so motivated to make an improvement here. So let's take a look. Because this is a recursive solution, what helps is actually drawing the recursion tree so that you can see things visually. So as you can see, I'm actually visualizing all the recursive calls here until we hit the base cases, right? And okay, so what's going to be the upper bound for such algorithm? What's going to be the big O-N notation here? So something that helps here, what kind of, like you need to ask yourself, what kind of tree is this? This is a binary tree, right? So worst case scenario, a binary tree, because we're doing worst case scenario, right? We're doing upper bound here. So the maximum number of nodes a binary tree can have is going to be this much, right? So that this is for a full binary tree. And a lot of you might already know the number of nodes here are 2 to the power of n, right? Therefore, if you want to count the number of recursive calls here, So that's going to be, so I have 2 to the power of n here because this is big O n, right? But if I want to be super precise, I should probably say 2 to the power of n minus 1, because the total number of nodes here are 2 to the power of n, but every non-leaf node makes 2 recursive call. And how many leaf node do we have here? 2 to the power of n minus 1. Therefore, that's going to be the most accurate one, right? Because I have 2 to the power of n minus 1 leaf nodes, and I have 2 to the power of n minus 1 non-leaf nodes in this tree. But because I'm doing big O notation here, it doesn't matter. So I'm just going to go with 2 to the power of n, and that's going to be the complexity of this algorithm. Therefore, this algorithm has an exponential time complexity, which is really bad, which is really slow, which is really impractical. Okay, we gotta improve this now. Memoization to the rescue. Okay, so how do we apply memoization here? So in order to apply memoization, the thing that we need to, because this is example number 1, so we're gonna go one step forward, and so the code is pretty similar to what we had previously. We still have the same base cases. We still have the same recursive call. The only thing that is different here is really when we save the result into memo n, and then every time we want to solve a subproblem, what do? We check, is this the first time I'm seeing this subproblem? If the answer is yes, then by all means, go ahead, make the recursive calls and solve the problem. But if I have seen this before, then I'm just going to get the answer. I'm not going to solve it again. I'm just going to solve every problem only once. So that's the only difference in this code. Now let's see how better or worse this might be compared with the previous one. Okay, so same recursion tree, right? But no, wait a second. We actually don't go through all the nodes with this code. What really happens here is when we actually check, so the condition that we have here, we check whether we have seen this problem before or not. A lot of times the answer is going to be yes. We have seen this problem before. We're not going to solve this again. And if you look at all this blue rectangular here, they represent the redundant work that we're avoiding in this version of the code. So previously, how many times we would solve the problem of Feb 0? Once, 1, 2, 3, 3 times. How many times we would solve the problem of Feb 1? 1, 2, 3, 4. How many times we would solve the problem of Feb 2? Again, 3, and so on and so forth. In this particular case now, we're going to avoid doing the extra work. We're just going to go linear, right? So we start with Fib 5, and then we go Fib 4, then 3, 2, 1, 0. And then for all other cases, we already have the answer. So what's going to happen here is if your n is 5, you actually have n plus 1 nodes in this subtree, right? And then you have two n minus 2 edges or 2n minus 2 calls, recursive calls. Therefore, that's going to give us a big O n as the upper bound for this particular code. Okay, how big of a deal is this? How much improvement did we actually make here? So let me show you one more slide, and this is mostly a recap from what we discussed before. So we went all the way. Our initial brute force solution has an exponential time complexity. We went all the way from exponential to linear. In case this is not obvious, this is a huge improvement. So we went from a completely impractical solution to a very fast, efficient solution for the exact same problem. And that only happens with the help of memoization. So that's the miracle of memoization and dynamic programming right there. But are we done? Not really. We are never done if we don't talk about bottom-up solution. Okay, so this is going to be more interesting and also more tricky sometimes. But how do we form a bottom-up solution? So first of all, I just want to show you again the recursive formula for this problem. So you see, if we have our base cases, the answers are known to us. If it's not a base case, then we have to make two recursive calls, right? So let me show you an example, and this is always going to help us to find to get a better idea of the structure of the subproblems. So I'm going to go with an example of memoized 5. So whenever, so this is, I'm just following the code that I just showed you in the previous slide. So whenever you actually called memo 5, what's going to happen? There's going to be two recursive calls, memo 4 and memo 3. And then for memo 4, there's going to be another two recursive calls, memo 3 and memo 2. And then for memo 3, we're going to have memo 2 and memo 1. And for memo 2, we're going to have memo 1 and memo 0. And that's it, because memo 1 and memo 0, both of them are base cases. So we don't actually have to make any further recursive calls here. Now, if you look at the order of the subproblems, what we did with memoized was going all the way from left to right, making all the recursive calls for n-1 and n-2. And this is exactly how we did our DP memoized version. Now, what other order going to make sense here? So if we reverse this order, something magical going to happen now. We don't really need to do any recursive calls now. Technically, when we are proactively solving the subproblems that we're going to need later. So we just magically know we're gonna start all the way from memo 0 and gonna go up, and we know that for whatever n we are trying to solve this problem for, we need the previous n's. So instead of starting from n and going down, we start from 0 and go up. And by that intellectual or intelligent reordering, we're going to get into a very interesting solution, and it's going to be here. So in this case, in this particular case, we're starting from actually for 0 and 1, we already know the answer, and then we're going to go all the way up to n+1, and every time that we are solving the problem for I, we already have the previous i's, i-1, i-2. So can we do even better? So if you realize the bottom-up solution is technically just a reordering of the subproblems, right? And we don't need to do recursive calls anymore. Those are great, but there is still something here then we can improve upon. And this is a question that we have to ask ourselves all the time. Could we do any better? All right. If the answer is yes, we need to do better. So now what I want to do here is, if you look at my code, what do I need all the time? I only need the last and second last values. So if that's the case, why don't I just create 3 variables instead of an entire array? I'm just going to create 3 variables, and I'm going to hold our second last value, our last value, and our current value with respect to our current term in the sequence when iterating. It's really as simple as that. So if I show you the code, this is probably going to make more sense. So we don't need any additional data structure now in this case. We don't need an array to store everything. What we do is we just compute the value of the current term, and we just actually have 3 variables to keep the current, the last one, and the second last one, and that's all we need. So another very important reminder here is, whenever you're computing a value in a sequence in an interview, just think about DP, because that's another great use case for DP. Now, my final optimized bottom-up Python code is going to be here. Okay, so I have A and B and C So those are my 3 variables. So no matter how large n is, I only need constant space. Previously, space complexity was O(n). So this has the same time complexity of O(n), but the space complexity for this algorithm is just constant. And that's the great benefit of this final piece of optimization we did here. So what can we do now? Wait a second. Let's go and submit this code on LeetCode and see how does this compare with other submissions that is already out there. So this is something I did, and here's the result. So the runtime of the algorithm was 0 millisecond. That is faster than 100% of the online submission for Fibonacci number. And also the memory usage was better than 91% of the submission, with some really little 2x and optimization. Sometimes you can actually push your code really far and achieve great performance. Now it's time for quiz. So I have a very actually simple question for you here. There are 2 functions to solve Fibonacci. And I have 2 questions, so you have to kind of guess what is what. So feel free to actually take a pause here and think about this question, maybe for a minute or 2, and then see if you get the questions correct. But the first thing I would like to suggest here would be recognizing which implementation are this. So you have 2 different implementation of technically the same solution, and we already did 3 or 4 different versions together in the last 10 minutes. So which one is which? Okay, so let's label them. The first one is the brute force solution, right? That we just had. So it's not memoized, it's not bottom up. The second one does something. So if you pay attention, the second one does the intelligent reordering. It does not check whether the problem was solved before or not, because it doesn't need to, right? Therefore, it's not the memoized version, it's the bottom-up version. We already went through the time complexity of both algorithms, so we know that the first one is extremely slow and the second one is very fast. Therefore, the answer to the first quiz question is that Fib1 for 44 gonna take, and this is actually shocking, 275 seconds. And then the second method, or the second implementation, actually takes 0 seconds. And then question number 2 is talking about the running time that we already know, exponential for brute force, and then linear for the bottom up solution. Recap. We turn to dynamic programming whenever we encounter 2 crucial conditions. We can break down a complex problem into smaller ones, and those small subproblems do overlap. So that's a green light for dynamic programming. But what if we don't quite understand the structure of the problem right away? What we do is we're going to look into how do we come up with a brute force recursive solution for that problem. It doesn't matter how inefficient it is, but that's going to help us understand the structure of the problem. Once we have established that, DB is the way to go. And then we have 2 main flavors to choose from. We have the memoized top-down approach, and then we have the bottom-up approach. Okay, so let's see another example here. Let's dive into a classic problem of dynamic programming, and this is called rod cutting problem. So this problem is a great example how dynamic programming can be applied to real-world scenarios. And also, we want to see how much or less practice with Fibonacci sequence comes handy here. Imagine you have a rod of length n and inches, and you want to maximize your revenue by cutting it into smaller pieces and selling them separately. Each piece has a price that is represented by pi, and then I is the length of the original length of your rod, which can be anywhere from 1 to n. Your goal here is to figure out an optimal way to cut the rod to maximize your earning at the end of the day. All right, so the first question we want to ask here, and that can kind of help us get a sense of the structure of this problem, would be how many possible ways for cutting up a rod of length 4? So how many different ways we can actually cut a rod of length 4? And 4 is a pretty small, reasonable size. So that allows us to kind of think about this more conceptually and visualize this. So I'm just going to show you all possible ways. So let's just try. And if you do, you're going to see that there are 8 different ways we can do this. So part A is representing a case where you didn't actually cut the rod and you're selling it as is. Part B is showing a case where you actually cut a piece of length 1, and then you have the remainder of the rod which has a length of 3, and you're selling these 2 pieces, and so on and so forth. So these are all different ways we can actually cut a rod of length 4. Now, let me bring up the price table that we had previously, and let's actually now see how good or how optimal each of these solutions are to this problem. So if we follow the strategy of A, how much revenue can we draw? So if we have one piece of length 4, that's going to be a revenue of 9. And then part B going to give us 1 plus 8, 1 for length of 1, and then 8 for length of 3, and so on and so forth. So there's going to be 1 revenue that we're going to draw for each of these particular setups. Now that we have all the possible ways of doing this, and we're looking at all possible revenues that we could actually draw, it's easy to say that the best setup here was actually setup C, and that is the maximum profit we can draw, which is actually 5 plus 5, which is 10. Now, I hope this example is kind of helping us to digest this problem better. Now, we're going to ask a more general question. How many possible ways for cutting up a rod of length n? Now, n can be any number, so this is going to be a little bit hard to visualize, but we want to come up with a formula that can help us tackle this problem better. Now, let me bring in actually a piece of rod so we can actually see something first. And then if you were to cut just this particular piece of rod, how would you do that? So if you're going to do this, probably you're thinking, okay, what are the areas I could potentially decide whether I want to cut or I won't? If you look at this, there is going to be technically, for this particular one, you can actually cut it anywhere, but I mean, obviously there's going to be a minimum length or a unit length, right? But other than that, you can actually cut it in a bunch of different places, except the very last one, because cutting a rod at the very end, it just doesn't make any sense, because that's where the rod going to terminate anyway. So now, this is going to be technically anywhere except the last particular cutting mark here. So there's going to be n-1 number of places. And in each of these positions, or for each of these cutting marks, you have 2 options. Whether you cut it or you leave it. So you only have 2 options. And then how many times you get that option? n-1 times. So that's going to give you 2 to the power of n-1 different cases. So now those are all possible ways of cutting up a rod of length n. Great. So now that we have a formula, this is going to help us big time moving forward. And then if you just try to, let's say, find the optimal revenue for all possible lengths of a rod, we're going to come up with probably a table like this. So if the rod has length 1, there's just one way of doing it, and that has to be optimal, right? But if the rod has lengths more than 1, then we're going to consider all different way of doing it, and then there's going to be an optimum solution, or there's going to be an optimal revenue for each original size of rod. Okay, so now I'm just going to shift a little bit to a different topic, maybe a more interesting one, or maybe something that people can relate to easily. And that's going to be, here's the question first. In addition to being a computer scientist or someone who enjoys coding, let's say you have a side hustle where you sell flower bouquets. And in this particular case, you have 6 roses with you. And you need to decide, how do you want to sell them so that you maximize your profit? So you technically have to regroup your roses in a way that you maximize your earning at the end of the day. Okay, so I'm not sure how do you do it, but a lot of you might be thinking of, or sometimes you're buying something that has a price table similar to what you're seeing here, and you're thinking, oh, maybe I should buy more because when I do buy more, I'm getting a better value per unit. So if that's something you were thinking, we are up to something here. Okay, so here's the idea. Let's find the maximum profit per rose for each of this configuration, and then we go with that option, and then we keep playing the same game with the remaining roses. Okay, so in order to make sense of this, let's go with an example here. In the example above, we start with, so technically what you do is $3, right? So you make $3 or $3 if you sell a single rose. So that's going to be the unit value, right, that we get there. However, if you keep doing that, for example, for 2 roses, we make $5. So 5 divided by 2, that's going to give us 2.5, which is lower than 3. And if you keep comparing the maximum profit per rose, or the unit profit of the rose for each of this configuration, it turns out if we sell 4 roses, that's going to be a better option, because that's going to give you the maximum profit per rose from the first place, which is going to be 3.25. And if you do that, you're going to be left with another 2 roses. And then you keep playing the same game. So with 2 roses left, you can only choose between the first 2 configuration. You're gonna go with the first one, right? And then finally you have only 1 rose left, and you have to go with the first option again. So in this particular case, the optimum profit that we received is 13 plus 3 plus 3. That's gonna give us a maximum of 19. But is this really an optimum answer? So this is going to be the topic of the next video, where we talk about a greedy algorithm, because the idea here and in this example indeed is a greedy algorithm that we just applied to this. But let's go back to the main problem we were dealing with, and which is actually quite similar to this particular side hustle situation. All right, so back to the rod cutting problem now. How do we go about this? So we need to kind of find an intuitive way of doing this, or we need to figure out what is the structure of this problem. And if you think about this for a while, you will see that with a brute force recursive solution, so we just want to come up, we don't want to do dynamic programming from the first place, right? Because if this is the first time you're seeing this question, it's going to be quite difficult to do that from the first place. What we want to do instead is we want to take our time, go step by step. And so first thing first, let's come up with a recursive brute force solution for this. Okay, so when we do recursive brute force solution, we are using divide and conquer. We don't care how efficient our solution is. What we do care is covering the entire problem space. So you just want to break down a complex problem into a smaller one. That's it. And in this particular setup, you might think, wait a second, how do I actually break down my problem into a smaller one? So the original size of the rod is n. So you have a rod of size n, and you want to cut it in pieces in a way that's going to maximize your profit. Okay, what if you start by cutting off a first piece of length, whatever. So let's say you start by cutting off a first piece of length I from the left-hand side or the left end of the rod. And that's going to leave us with a right-hand remainder of length n minus 1, n minus I. Importantly, we further divide only the remainder, not the first piece, because you made your mind there. And you're saying that, okay, I'm cutting this at length I, and that's going to be one of my pieces. And that's going to be my piece number 1. And that's part of the final optimal solution. Now, you might say, but I don't know. How do I do that properly? Or what's going to be the best place for me to length? What's going to be the best value for I? Well, you don't need to. We are doing divide and conquer, so we can try all possible values for i's. Therefore, this way of thinking allows us to express the solution with no cut at all as well. So technically, we're going to cover all different cases. If you don't have any cuts, that means your first piece has the size of the entire road. So technically, the first place you're making a cut is n, right? And then that's going to correspond to the revenue denoted as P of n. And then as for the remainder, we assume that it has the size of 0, because technically you don't need any other decisions, right? Because that might sound obvious, because a rod of length 0 actually does not exist. Is technically not a rod, and you can't be selling that for any amount of money. So this way we are breaking down a complex problem into a smaller one. What is a smaller problem here? R of n minus I. So that's the sub problem we have. R of n was your original problem. With your choice of making the first cut, we are breaking the original problem into a smaller one, and that is of size of n minus I. So I want you to pay special attention here how we are doing that. Okay, so putting this together, that's going to give us a very simple solution here. So let's take a look. So this is how it works. So if you have a rod of, so that's my base case. If you have a rod of length 0, you won't be able to make any money. In all other cases, what you do, you first make a decision on your first piece, and then you're going to recursively call the same function for subproblems of size n minus the length of your first piece. This is obviously divide and conquer problem solution, and this is obviously going to cover every single situation in our space. So think about this. If you can find a subproblem that this solution doesn't cover, that means we are wrong, right? But I hope you won't be able to find, because there isn't. Anyway, so now for this particular solution, as always, we want to kind of look into the recursion tree, and we want to make sense of the time complexity of that recursion tree as well. So let's do that here. And so the recursion tree for this one is going to look a little bit different. So previously we were dealing with Fibonacci series. If you remember, we were looking into binary trees, and this is not a binary tree, obviously. So here's the recursion tree for our first recursive brute force solution. The root of the tree refers to the original problem of size n, which in this example is actually size 4. And then that's going to be our very first recursive call to the root. And that's where things kind of get us started. And then every other nodes here are representing a subproblem. A subproblem of a smaller size than the original one, right? Okay, so let's make sense of this edges here and see what happens when we are looking at different edges, when we move from one node to another node. So the first example here is what happens here. So this is a case where we made the first recursive call to the root, and that was for the original problem of size 4. And then remember, the way things work, we make a decision on the first piece. So we're gonna make the first cut. We're gonna take that first piece, and then we're gonna try to solve the problem for the remainder of that original rod. So in this particular case, let me picture it for you. This is exactly what has happened. So we actually caught a rod of length 2, and we set that aside because that's part of your optimal solution. And then for the remainder, we are trying to solve the same problem again. So what's the remainder? So remainder is another rod of length 2, right? And what are the options do we have there? Keep it as it is, or cutting it into rods of length 1, right? And this is exactly what's happening, what's going to happen down there on that branch. Okay, so let's take a look at another example here. So when we go from 3 to 2, what's the physical meaning of that? That means your subproblem, you were solving a subproblem of size 3. You made the first cut, you made a piece of length 1 with that first cut, and then now you're solving the problem for a subproblem of size 2. So let's picture it again. This is exactly what we're doing here, right? So each of these actually edges here are showing one possible ways of cutting the rod. Okay. So the next thing we want to do is the time complexity of this particular algorithm, because we always want to know how good we are doing, right? And for this particular one, I'm just gonna start with the recursion tree first. So the first thing you might notice here is that you have a single call to the root, and that's your very first recursive call to get things started. So we're always going to have one single, regardless of the n, we're going to have the size of your original subproblem. We're always going to have one recursive call to the root. And then what else? The other thing here is now we need to see how do we solve each of those subproblems of size. The way we formulated this problem is going to be n minus I, right? I is the length of the first cut, and then n is the original size. And then the remainder of the problem always going to be, your subproblem always going to be n minus I. Now, if you look at this formula, it looks a little bit scary, and it has two parameters, and it's kind of hard to solve this or make sense of this. So I'm going to do, I'm going to change the variable. I'm going to do a change of variable here, and I'm going to explain that. So we have t of n minus I. I can be 1. So if I is 1, that's going to be t of n minus 1. If I is n, that's going to be t of 0, right? So we're going to have t of 0 all the way to t of n minus 1. So if you're okay with that, then I'm just going to do a change of variable, and I'm going to go with t of j from 0 to n minus 1. So these are exactly the same problem to solve, right? Okay, now, how do we solve that tj? So that's going to be the next thing here. How do we solve that t of j? So for this one, we can actually do a little bit of a work here. So as you can see from my recursion tree, I have, for the original size of tree of 4, I have one call to cut rod 4. I have one call to cut rod 3. I have 2 calls to cut rod 2, and then 4 calls to cut rod 1, 8 calls to cut rod 0. So that is what's happening here, right? So you probably can see the pattern already, because what we're looking at here is technically an exponential growth in terms of the number of the calls with respect to the size of the original problem, right? And so we always have that first call to the root, right? And after that, it's 1, 2, 4, 8. And you can easily see that it will be 16, 32, 64 moving forward. Therefore, some people do induction proof here, but you actually don't need to. And let's actually solve this equation now. So instead of t of j, I'm going to put in 2 to the power of j. And now this should look familiar, right? So all we need is sum of geometric series. So I have the formula for you right here. And then just plug in this formula, identifying our A1 and R. Then we know that this can be evaluated to the power of n. So that's a good news. Like, first of all, we solved this. We know what is the running time complexity of this algorithm. But the bad news here is that this solution is super, super slow and very impractical. And therefore, we need to, guess what? We need to continue with dynamic programming to hopefully find a better solution for it. So the memoized version is going to be the first thing we're going to try. And it's going to be very easy at this stage because, like, we already done a good job on understanding and identifying the structure of this problem. So with memoization, we do exactly what we did with the recursive brute force. The only thing is, just like last time, we're going to check whether we have solved this subproblem before or not. So if you're dealing with what is the optimal value of size, let's say n-5, the first thing we're going to do, we're going to check, have we ever solved this problem before? If we did, we're just going to retrieve the answer. If we haven't, we're going to go ahead and solve that subproblem. Okay, so I want to also visualize this in case it's not clear with the code. But if you look at the code, you can kind of see that what we have here is each subproblem is solved exactly once. And in order to solve a subproblem of size A, what we are doing here is we are running through I iterations of the for loop. So the total number of iteration of the for loop over all recursive calls forms an arithmetic series. Okay, this might not be good enough for some people. So let me actually show you this visually. So in our memoized version, we are solving each subproblem once. We start with a problem of size 4, and then we're going to do 4 recursive call for that one, right? And then we do subproblem of size 3, and then we do 3 for that, and then we have 2, we have 1 for subproblem of size 0. The answer is obvious. That's a base case, so we don't need to do recursive call. But at the end of the day, it should be easy for us to see that we have n+1 nodes, and the number of edges here are going to be n plus n-1 plus n-2 all the way to 1. And obviously, yeah, to 1, right? So there is no 0. And so this is going to be the arithmetic basically series that I was talking about in just 2 seconds ago in the previous slide. So now this is going to be the total number of recursive calls we have to make in order for this memoized solution is going to be n times n+1 divided by 2. So this is going to be therefore a quadratic solution, which is again, so it's not linear, right? But it's quadratic and it's still better. So it's not as good as linear, obviously, but it's still a huge improvement from the exponential solution that we just had. So the interesting part here now is going to be our final DP attempt. So how do we reorder this problem so that we don't actually, not only we don't solve the same subproblem more than once, but actually we don't even need to check whether we have solved this subproblem before or not. And that's where we have to kind of kind of do the opposite, go from the opposite order. So what we do here is we proactively compute the solutions for smaller rods first, because we know that the solution to smaller rods are going to be part of the solution to the larger rods. Therefore, we're going to start all the way from the minimum size of the problem, and we're going to go up and proactively compute a solution to all of these subproblems. And with this reordering, then we actually guarantee that we are not solving a problem more than once, and also we are making sure that we don't even need to check, because we don't even need to check if we have saw this subproblem before. And now, if we put this together, we need to do one little thing, and that is because if we want to actually find the optimal way to split the rod, instead of just finding the maximum profit we can create another array S, and that S will basically, so let me put it this way. So we can create another array S, and then let Sj be equal to I. And if we determine that the best thing to do when we have a rod of length j is to cut off a piece of length I first, then that's going to help us to print out the optimum way of actually splitting the rod. So we're going to get everything printed out. So I actually have put everything, I coded up this solution for you already, and I have the link here, and this link is going to be in the description as well. And so please feel free to take your time and run this code, and then we're going to continue with one more interesting problems where dynamic programming can help us find a very effective solution here. Another fundamental and classical problem where dynamic programming can shine is the problem of longest common subsequence, which happened to be a LeetCode question with medium level of difficulty. So picture a strand of DNA, which consists of a string of molecules called bases. These bases come in 4 flavors: adenine, cytosine, guanine, thymine. Now, the fascinating part here is that we can compare these DNA strands to determine how similar they are, which can give us insight into how closely related two organisms might be. So we have various ways of defining such similarity, and one of them involves finding a third strand, let's call it S3, in which bases of S3 appear in both S1 and S2, and then the key here is that these bases must appear in the same order, but not necessarily consecutively. So they don't have to be back to back, but they must follow the same order. All right. So with that said, we want to find the longest common subsequence between 2 sequences of DNAs, right? And so the problem here would be, and then probably the most difficult part of solving this problem is going to be, how do we find, how do we break this complex problem down into a bunch of subproblems, right? So therefore, the first step to solving this using dynamic programming, because this is indeed an optimization problem, right? So in case you didn't recognize at the beginning, this is obviously an optimization problem. We want to find a common subsequence that has the maximum lengths, right? And so how do we actually do that? So there might be a bunch of different way of doing it, but this is definitely the hardest part of solving this problem. How do we decide what are our subproblems? So the key here is you want to generate all possible sequences, right? So you want to consider the entire problem space, but we don't care how efficient that process might be. We just want to check everything, but it doesn't really matter how efficient it is at this point, because we just want to identify the structure of the problem. Then we're going to tackle the inefficiency with the application of dynamic programming. Okay, so there might be a few different ways this can be done, but probably one of the most common way of solving LCS is breaking it down into two, or I can also say three, but the idea here is, let's look into our two subsequence, or sorry, let's look into our two original sequences, and I'm going to call them X and Y here, and previously we called them S1, S2, and now we are calling them X, Y, Z. Z is going to be the longest common subsequence, and X and Y are going to be our two original sequences that we're gonna examine. Okay, so you want to find the longest common subsequence. If the last element of X and Y are exactly the same or equal, then they both, because they are the same, right? They must both be part of the longest common subsequence. So we can drop both elements off the ends of the subsequence, and then we add that element, that common element, to the longest common subsequence so far. And then we solve a smaller problem. What is the smaller problem? We find the longest common subsequence of X and Y, excluding that last element. So that's one case, right? Now, if the last element of X and Y are different, then something we can say for sure, you might say there are a couple of cases here, but something we can say for sure is either the last element of X or the last element of Y cannot be part of the longest common subsequence. Maybe both of them, right? But at least one of them can't be. So now we can find the longest common subsequence of X and a smaller version of Y, or the longest common subsequence of Y and a smaller version of X. When I say smaller version of X, the original X excluding the last element, right? Okay, so if you break it down into subproblems like this, then I think the rest from here is going to be more playing with the problem a little bit, visualizing it, finding the right ordering, and then applying dynamic programming. But this part was obviously the most difficult part, and oftentimes it takes lots of practice so you can come up with such a solution, such a brute force recursive solution from the first place. But now what we can do here is, and by the way, there are proofs, there are lots of proofs why this is actually the right way of doing this. And this is not the only way of doing this, but there are proofs why this is correct. But I'm not going to get into the proofs behind this here. So now what we want to do is, okay, so we do already have our brute force recursive solution to solve this problem. And here's the formula. And first of all, let me define, we have to kind of reformulate things a little bit to make it easier. So what I have here is, we want to compute all values of Cij, which are the lengths of the longest common subsequence between the first I elements of X and the first J elements of Y. So we want to be clear here. When we say Cij, that means LCS for first I elements of X and first J elements of Y. All right. So now what you can see here is if the lengths of both X and Y is 0, then obviously the longest common subsequence can't be anything longer than 0. And then we have two other cases that we just discussed. And if the last two elements are the same, then your subproblem is going to be finding the LCS for a smaller version of X, a smaller version of Y. And otherwise, if the last elements are different, we're gonna explore the longest, we're gonna look for the longest common subsequence in either x and a smaller version of y, or a smaller version of x and y, right? Okay, so that is the structure of the problem that we're dealing with. Now, we just need to find the right order. How do we do this more intelligently so we don't really, so we make sure that we don't really solve the same subproblem more than once, and we don't even need to check whether we are solving the same whether we are solving all the subproblems, right? Or whether we solved the same subproblem before, or this is the first time we are seeing it. So if you find the right order, then none of this are going to be a concern. Okay, so for proactive solution here, what I'm going to do is I'm just going to show you, or I'm going to first see, what do I really need? What are like all the things in the world that I need in order to calculate C of I and J? And the answer, just looking into the formula a little bit, the answers are going to be three things. We need C of I minus 1, J minus 1, and we need C of I, J minus 1, and C I minus 1J. Okay. Therefore, I always need three things. And because this is now, so what I really need to notice here is, previously the size of the problem was always n. Here the size of the problem is I plus j. So that's technically going to be, you can say n1 plus n2, right? N is the length of your first DNA sequence, and n0 and n1, and then n2 is the length of your second DNA sequence. So here what we have is I and j, right? And so I plus j is the size of your problem here. And therefore, we have a two-dimensional problem. This is not one dimension anymore. So I can actually go with a table here, with a tiny little 2x2 table, and I can say, hey, what all we need here is the top cell, the left cell, and the top left cells, right? So these are the three things you need in the word in order to be able to find the answer to C, I, and J. Okay, so we pretty much have everything. We just need a little bit of confidence to put things into the work. And we can do that here. So you often see, when it comes to longest common subsequence, you often see a table like this. I'm going to put it in the background for now because I want to bring that 2x2 little table here and want to show you what's going to be the right order. So right now, if you want to find the answer to C1 and 1, you already have everything you need, right? So we're going to do this, and then which direction can we possibly go to the right? And we're going to populate this table one by one, and then we're going to go to the next row, and then we keep going that way. And finally, this is the horizontal traverse scanning pattern that we're going to follow here in order to actually populate this table all the way from ground up, without a need for any recursive calls, or without a need even to check whether we have seen that particular subproblem before, yes or no. Okay, so now you see a bunch of errors here. That is probably the confusing part of the solution, the only part. But worry not, those errors are just for us, are just some clues for us to print the longest common subsequence. Whenever we found the answer, obviously we also need, we don't just need the length of that longest common subsequence, right? We need the actual subsequence. And these errors are just technically going to help us in order to print that out nicely. Okay, so finally, what I have here for you is a super quick quiz. So consider the two words that I have here, algorithms and logarithmics. And what I want is, I want you to see a demo, live online visual, so you can see how this algorithm that we were just talking about, the bottom-up dynamic programming algorithm for longest common subsequence, actually work visually in order to find the LCS in this particular example. And there you have it, folks. We reached the end of our exploration into the captivating world of dynamic programming. I hope you found this journey as enlightening as I did. Dynamic programming isn't just a technique. It's a problem-solving mindset that can open doors into new possibilities and more efficient solutions in your coding adventures. But remember, learning dynamic programming is not a one-time task. It's a skill that grows with practice over time. Don't be discouraged if it feels challenging at first, because it does. Keep at it, and you will see the rewards in your problem-solving abilities. Until the next video, where we unpack greedy algorithm, which is another fascinating problem-solving techniques, keep coding, keep learning, and keep exploring. This is Ryan Rad signing off. Take care, and I will see you in the next video.